Have you ever wondered what actually happens inside a nerve when it's injured and how it tries to heal itself? Let's take a journey through the step-by-step process of peripheral nerve injury and regeneration, a fascinating story of cellular teamwork and repair. When a neuronal axon is injured, the first response is a temporary increase in axonal permeability to calcium ions. This calcium influx creates a rapid concentration pulse at the damaged end of the axon. The rise in calcium helps the cut axonal end seal itself by forming a retraction bulb, preventing further leakage and stabilizing the membrane. Next, calcium activates a protease, calpain, which digests the submembranous pectrin cortex. This digestion allows new receptors and membrane components to reach the axon tip surface, an essential step for regeneration. Following injury, a retrograde or proximal degeneration occurs, extending at least one internodal space from the site of injury. The extent of this degeneration depends on degree of the proximal injury. The next phase is temporary condition of regeneration in response to harmful stimulus, with increase in the synthesis of cytoskeletal and other housekeeping proteins and downregulation of enzymes related to neurotransmitters. The cell body undergoes characteristic morphological changes known as chromatolysis, which include disintegration of Nissl substance into dust-like particles, peripheral condensation of the remaining basophilic substance, eccentric displacement of the nucleus, which occurs because Nissl-free cytoskeletal components are stockpiled, not because of apoptosis. Then there's formation of basophilic nuclear cap with a crenated nuclear lemma. Small basophilic satellite glial cells around the injured neuron become activated, a phenomenon called satellitosis. These cells are believed to provide neurotropic growth factors and support neuronal survival. During this process, there is a temporary loss of presynaptic dendritic terminals at the injured neuron. For regeneration to succeed, the distal axon segment must be cleared because its remnants are inhibitory to regrowth. The degenerative changes distal to the site of injury are called Wallerian Degeneration. Several coordinated cellular events follow. This is where myelinating Schwann cells switch to a demyelinating phagocytic phenotype. And then there is macrophage recruitment. Bone marrow derived monocytes cross intact blood vessels into the injured peripheral nerve. The paths of degenerating and partly phagocytosed myelin are left behind as ovoid droplets. Recruitment begins within 2 to 3 days, peaks around 7 days, and macrophage influx continues to rise, reaching a maximum by 3 weeks. Macrophages clear the remaining myelin and axonal debris using opsonins, complement protein, antibodies, and pentatrixins. Once the debris is removed, Schwann cells migrate along the surface of polarized blood vessels in the nerve bridge, helping direct the axons towards their targets. Schwann cells undergo mitosis and multiply and then align the basement membranes to form tube-like structures called bands of Bungner. These bands act as guidance channels for regenerating axons. They secrete neurotrophins like brain-derived neurotropic growth factor or other neurotrophic factors like NT3, NT4, 5, NT6, other growth factors like insulin-like growth factor, ciliary neurotrophic factor, glial cell line derived neurotrophic factor, neuregulin 1, and adhesion molecules like neural cell adhesion molecule, N-cadherin, and integrins help in axonal guidance. At the target site, specialized terminal Schwann cells direct the axon towards its original innervation zone. Finally, chemotactic cues from the effector organ help guide reinnervation. Muscle tissue is more effective in promoting reinnervation than skin or sweat glands, which explains why motor recovery is often better than sensory recovery. The regenerated axons are usually remyelinated, but the new myelin sheaths are often thinner and the internodal distances shorter. This results in slower conduction speeds compared to the original axon. So from the first calcium surge to Schwann cell guidance, nerve regeneration is a carefully orchestrated process of repair, cleanup, and regrowth. And understanding these steps is key for anyone studying neurology, physiology, or medicine.